Okay, so let's go back to the driver, and let's suppose that now that I put Fred into the table, I want to see if Fred's in the table. What information, what am I going to ask the worker table? Dot, we haven't written it yet. We'll call it get or retrieve or whatever it happens to be. What information are you going to supply? Just the key, right? So the key is going to be what kind of thing? Worker. It's going to be a worker. If we were to make one, what would that thing be? The easiest thing is we could just say it's Fred, and then we could do a tell me whether or not Fred is in the table. Okay. What's the trick here? There's something that's not quite right. What's our rule for searching? You got to use something that looks like, because if you had them, you wouldn't be searching for them. So what kind of thing is going to look like Fred? A new worker with what sort of information in it? Depends on the what in worker. In the old days, we would have said it was the equals in worker. But what is Fred using to place himself in the table at this point? The hash code. Let's go look in the worker class and see what's being used. It's just the name, right? So hash code works just like we've seen with equals, right? You only give partial information to the hash code, and all you really care about is, in this case, is his name. So when we go and we write our fake guy, the fake guy that we're going to write has to match Fred. But we could care less about the other value. And now we'll go see whether or not we can retrieve Fred. What are we going to get back? A worker object, which is hopefully the found Fred, in order to retrieve him. Let's go into hash table and write the get method. So it's going to give back an E-type thing, or actually in this case a value type thing, get, and what we supply is just one of the two things of the pair. So I'm going to give you the key back. I want you to give back the value that's grouped with that thing. Okay. E item to return. Set it to null, or V, sorry, for the value. Item to return is null, and we'll send that thing back just to make the compiler happy. And then we'll figure out how to retrieve it. So we've got the key. What are you going to do to retrieve it? The magic is actually look at how you put it into the table.
Find the position.
So the first thing that we're interested in is we need to talk to the key and say, give me your magic number. Okay. So in the case of, that might be social insurance number or whatever, so we'll borrow this line of code. Now what? It gives us some arbitrary number. Same thing. The problem with that number is that it might be too large for the table, so we'll scale it back to the table position just like we did before, and then we've gotten the position in the table. So there's the item that we need. I'll just put this into this way. Actually, I won't. here. Actually, do it. Why doesn't it like that? Yeah, it's the wrong type of thing. The table holds nodes, and we're not interested in nodes. We're interested in this case, workers. So in this case, the thing that you get out of the table is a node. So we'll go get the node from that particular position. So we got that thing. What's the thing you want to send back?
The object.
The node's value in this case, right? So this is going to be v value is talk to table node and get the thing portion of it, which is the value part. I think I did that right? No? Thing dot value. There we are. One level off. Actually, let me separate this out for you. If you get a node, what does the node refer? Or sorry, you get a table node. What's the table node dot thing portion? It's the pair. So this should be. Oops. Go away. And then we'll return item to return dot, or sorry, a pair dot value. We'll ignore item to return for a second. It looks complicated, but it's just the reverse of how we put it in. When we stuffed the thing into the table, we made a pair first, and then stuffed it into a node, and then put it into the table. So if we're retrieving things, we go to the table, we get the pair out, or so we get the node out, and then we get the pair out of the node. So it's exactly the reverse of how we put it in.
What is V? Is it an object, or is it like a data type, or what?
The pairing here is either, in this case, we're associating a worker with a worker. So this is the key, and that's the value. Or in the case, sometimes it's going to be a string with a worker. So that's the key, and that's the value.
I think he's asking what V actually is as opposed to what it's containing.
Value. No, I get it.
It can be anything, I guess.
It could be anything. So you could, so it doesn't have to be a worker. It could be a student. It could be another string. You could associate two strings together. So it wouldn't be unusual, like a dictionary associates a string, which is a word, with a string, which is the phrase that describes the word. Okay, so you could have a hash table of string would be perfectly fine. Okay, so the joy of hash tables is this idea is that they're always pairing things together, a unique thing with some other thing, at least temporarily. Let's see if I got all my bugs out. Okay, and so if we've done this correctly, let's just see whether or not we get the right thing back. And I'll just double check in the worker class and make sure that it's got a toString. Yep. Let's just run this thing and see what we get. And if we're lucky, it should print out found Fred's information and not die, but oops, it died. Why did it die?
Something about the cast.
Something about a class cast exception. Something about hash tables nodes, and the line that dies is the main program calls the constructor, which is what that init refers to. So it's that line that's dying. So the line is dying because it's saying, if we scroll over here, it's saying you can't cast that object thing to a node like that. This is another Java weirdity. You can't make, we've already had to change this and said, well, we'll make an array of objects and then we'll cast that into node, but the Java runtime doesn't like that. So notice it didn't catch it as a compile time error. The thing that you have to do here is you have to use, there's an array class where you say array dot new instance, and you give it the kind of thing that you want to store in the table, which in this case is nodes, and the size of the array that you want. Okay. And array.newInstance is a little weird because notice it takes the compiled node class as an argument. So it's just a weirdity, a Java weirdity. Whenever you want to allocate an array of nodes, that's sort of the way it's done. And my error message says, yeah, that thing has to go away. There we go, thanks. Right, and it'll still generate a warning saying, hey, you're trying to turn nodes in, or objects into nodes, but it'll work. Okay. You still have to cast it because by default the thing that it gives you back is, even though you've said it's a node class, the signature that is the standard one says you get an object array back because it has no way of saying you get a node back. That would change the signature. So yeah, it just has to be done that way. Try our driver one more time now that we've gotten rid of that little weirdity, and we managed to put them into the table and get them back. Okay, no big surprise there. That's the short version of the code where we don't have to worry about any special circumstances. Okay, so now what's going to happen as a special circumstance? No, I'm missing something. Oh. What's going to happen as a special circumstance when you put somebody into the table? What's the gotcha? There's somebody already stored in that position because why would they be stored there? There's a collision with, if this were social insurance numbers, they happen to have the same last two digits of the social insurance number. So they also want to occupy that table position. So now what do we do? So we've got this chain of things, and now you have to worry about, is there somebody there or not? Where do you want to put them on the chain? You could put them at the end. Any advantage to putting them at the end, or disadvantage? Got to walk through the whole list. Is there any reason why we have to put them at the end? So putting them at the beginning is actually just as good, because the whole thing that we're trying to do here is not get things in any order. Order doesn't matter. We said the other day that since these are sprinkled all over the table when they come in, if you go through and iterate through the table, you get random order anyway. So it really doesn't matter whether we put this guy before or after in the chain, and the easiest place to put him is to link him in before. Okay, so how would you link them in? How would you link this guy? Suppose we have another node in here with its pair, associated pair there, and you want to link that guy in. We'll give this one names. This is table sub whatever, and this is new node, whatever we happen to call it. How would you get new node linked into there?
Get new node to point to the original node first, and then make it so the array points to new node after that.
So new node's next needs to refer to whatever the table thing is referring to, and then table sub whatever gets new node. No, let's just give that. We've already got table gets new node, so all we need is a node dot next refers to what's already in the table, and then table sub whatever gets linked in. Does that work for the empty case? If there's nothing in the table? If it's null, table at that position just gets, the null just gets dropped into the A nodes next, and then the table at that position refers to it. So it happens to work for the empty position too. It's a little bit slimy. If it were me, just on general principles, I would probably kick out the null case and just deal with it in an obvious way, but that will work for the null case to link them in. Okay, so it's real easy. Anytime that it doesn't matter if there's somebody in that position already, you just link them into the front of the chain. If the chain's empty, it works. Just one line of code gets them linked in. Okay, well there we've put them into the table. Now what happens to the retrieval case? When you go to retrieve somebody and somebody says, is Fred in the table? What does our current code say? Just look at the first one, but that's now wrong because Fred is there, but he's actually the second one. So what do you have to do now to make sure that you get Fred? You have to look through all the nodes and compare what? Careful here. Compare the keys, because they'll have different keys. So like if we were saving Fred's social insurance number as the key, then when we found the same social insurance number, we would know that it was the right guy. So the reason we kept both the key and the value is so that in the case where we get multiple things on the chain, keys are unique, so we can go use the keys to find out which one it is. Okay? So getting the right table position doesn't ensure that you found the right person. You got to run through the chain and look and compare all the keys to see whether or not you found the right thing. Okay? So let's just do that. Here's our retrieval thing. We went through and we found the thing at the table position, but now at this point we don't necessarily know that that's the right one. So how often might we have to do that? More than once, right? So that means that portion becomes essentially the loop. We found their table position, and now we're going to run through all of the things at that position. So while table node is not equal to null, we would attempt to do that. More or less. Not quite right yet. And then worst case, we didn't find them. We would explicitly say no. Don't need that variable anymore. So there's the first one. We've grabbed the thing. What do you have to do here? You have to check to see whether or not that's actually the correct one. So we'll run the chain, see if we found the correct one. How do you know if it's the correct one? If the keys are the same, so let's leave that line up there, table node dot thing. If a pair dot key matches, how are you going to say matches? Well, there's two choices here, right? It either matches with double equals, which is to say it's identical, or dot equals that key.
Key dot key?
Well,
Oh,
no,
no,
just key. And so this one, it's actually probably easier to write the other way. If the key, just to get rid of a dot here, matches a pair dot key, oops, then at that point we can say let's return that one. That's the special case. Otherwise, didn't find it, what do you have to do? Go to the next node, so table node equals table node dot next. Advance to the next node. Okay? So start out at whatever position in the table is appropriate, go through however many things are there, possibly none. If you find a matching key, then you found the correct person and you can return the value that's associated with it. Otherwise, you just bump along to the next one. Eventually, you either find them and return their value, or you run off whatever's on the chain. Okay? So now we can put two similar people in the table. So let's go back into the worker class just for fun, and let's make it a little bit more obvious. I'm going to add int social insurance number really quickly. Just because this will make it maybe a little bit more obvious. And I'm going to change the hash code to just give back social. I'm just going to manipulate my test data here a little bit. And then this guy doesn't matter because we're not using him yet. But here's founder Fred, and I'm going to give him a social number of I guess 57, so that he fits into the table. And the one that we're looking for now, I'm going to change to be find somebody who has that social insurance number. So there's that idea of finding somebody. And then I'm going to put in an extra one. So not only will I put Fred into the table, oops. Oh, let's just eliminate this one so I don't have to deal with it. Oops. I got rid of too much. Let's just grab this guy and slide him down here. Get rid of a little bit of the string stuff, just so it's less annoying. And when we put Fred in the table, we'll put him in with social insurance 57. And just for fun, I'm going to add a second worker. And I'm going to put, I'm going to make a different worker who has a similar social insurance number. So we'll make not Fred, and his social insurance number is that, which is still two different guys, right? And we'll put not Fred into the table also. I think I got that right. With a semicolon. Okay, so the idea in here, there's one Fred with one social insurance number. Here's another Fred with a totally different social insurance number, so they're unique individuals. And then I'm going to drop both of them into the table.
You just need not Fred, comma not Fred.
Oh, okay, not Fred. There we go. Okay, and they're working off of social insurance number, and then I'm going to go through and say turn around and retrieve them. Okay, and I would expect in this case that not Fred would get inserted before Fred, because the way we put them onto the chain. But what should happen is it should run the chain and find the second one that matches. dot get search key, thanks. And hope that it's the right one. Just out of interest's sake, let's see which one we get. Didn't find him. Gotta hate a mystery. Let's just go into our hash table class and let's put a breakpoint on the place where we're trying to find things. And let's just run with the debugger for a second and see what it does. So here's the point where it's trying to find stuff. We'll do a step over there, and it says, well, table node is not equal to null, so it's searching for something. We'll do a step over. Let's see if I can show you what we've got. There's the pair broken out, and then if we look at the key in the pair, the key has a value of Fred, president, with the 4457. So that's the second one that was inserted before the first one. Okay, so those keys don't match. Do another step over. Goes and does the next one. This should be the matching one. There's definitely something in that chain because it's found the second thing on the chain. It digs the pair out, and then if we look at the keys for the pair, there's Fred, president, 57, matched with the fake one that we're giving, which is called, let's just double check, which is just called key. So the value for the key worker is nothing, nothing, 57. So it looks like we're matching 57 against 57. Do a step over, no match. Yeah, notice.
Oh, isn't it using name or something?
No, notice that what we used here, yeah, we used a dot equals here, okay, to find out whether or not something was actually there. Let's just go back into the worker class and see what the equals does. Equals, 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 the default. What's the default for equals? Memory address.
Oh, right.
Okay, and so the problem is that we should actually have an equals in here, public Boolean equals and this is worker other equals worker what, and then return, what's the thing that's matching? Social, same social insurance number. They're the same if their social insurance numbers match for equals. Notice something interesting about wanting to put things into a hash table. If you write your worker, student, whatever class is, in order to use it in a hash table, you have to not only write the hash code method, but you have to also write the equals method. Because the hash code method is used to tell you what table position you're going to occupy, and the equals method is used when you run the chain to see whether or not the keys match. So if you use worker as a key and as a value, then because it's a key, you have to write hash code and equals. Okay? So as a general rule, from now on, anytime you write your classes, in addition to writing all of those other methods like getters and setters and constructors and toStrings, if you ever plan on having your base object used in a hash table, you have to write the hash code and equals. There's the simple rule. Why does it work for string, by the way? You can put strings into the table. I took that one out, but we had an example of just using strings. String already has a hash code and an equals. Okay? So string takes care of itself. So that's why in a lot of hash table examples, you'll see them use string against string. I'll put a string into a table and I'll match it against another string as a value. That only works because string happens to have that stuff built in. If you ever use something other than string as a key, you better have that stuff in there or it won't work.
I was wondering for your equals signature there, why can't you just say worker right from the beginning instead of passing it over to?
Because equals officially allows you to check to see if things that are not workers in this case match a worker.
Right.
So you can check a cat against a worker to see whether or not they match. And the answer by default is if they're not the same type of thing, they're not a match. And so officially with equals, what you're supposed to do is you're supposed to have an if statement in here that says if what instance of whatever it is, worker, and we'll do the rejection here. It's not an instance of worker, and for some reason they chose to spell instance of that way. I think I got that almost right. Yeah, this has to be in parentheses just to do it. Something like that. Okay? Officially, if you write equals, that's what you're supposed to do. So that says kick out the things that aren't obviously workers as obviously not being a match, because somebody could try to match. I never do that because this will just quietly return false, but in actual fact, someplace up above is somehow deciding that it needs to compare cats to workers, which is probably a bug. Okay? And so if you leave this out, what's going to happen is this cast is just going to make it die, which is the more appropriate thing. You shouldn't be comparing cats to workers, and so we're going to kill you off, and you can go figure out who's doing that silly thing. Okay?
So what do you mean by official? Like that's the like.
This is if you follow the documentation for writing equals method, it specifically says this is what you're supposed to do. But in general, it's a very bad thing to do, because most of the time you would never ever want to do that. Because if you leave this false here, what happens is someplace in somebody's code, somebody could blindly be comparing cats to workers, and it just says false, and they think that that life is good, right? Oh, okay, it just didn't match, oh, whatever. But in actual fact, that whatever is a problem that should be dealt with. Okay? So the signature has to be object, because officially you're allowed to match anything to anything. Okay, so we'll just take that out. Okay, so back to the simple rule for hash tables is that whenever you write one of these low-level classes like worker or whatever, the best thing you can do for yourself is just turn around and put the correct equals and hash code methods in there, and then it'll always work for hash tables if somebody decides to use it for that. Or alternatively, if you don't put it in and you go and you search for something and you can't find it, chances are pretty good that you didn't write hash code and equals when you go to use it in a hash table. Okay? So they basically have to be there. Anything can be put into a hash table because the default for hash code is your memory address, so that makes things unique. But if you're planning on using those things as the key in your table, then you need to have equals in there. So generally it's just a good idea to write both. And the other little known thing is that they should always agree and use the same fields. So for instance, for student, if you say first name and last name are things that make this name unique, and the student unique, and you write your equals with first name and last name, then your hash code should also use first name and last name for hash code. They have to agree, because if they don't, you're saying this is their identity one way, but they're somehow unique in another way with a different identity, so you're not allowed to do that. Okay. When all of that is said and done, we can now turn around and find the correct person in the table. One last thing to do to this for our hash table. Suppose that in my driver I do this. Worker table dot put new just grab this thing and dump it in here. Fred gets kicked out of the union. Well, he gets demoted, at least. Okay, I almost did that right. Oh, I'm gonna have to put that, I'm using worker, so just let me. We'll take him and we'll dump second Fred into the table. Like so. Now what do you do? What's the right thing to do here? That's the question, is do you want to replace him or not? Why or why not?
Well, he's actually saying that you don't want him to replace.
Yeah, but you'll find the first instance of them anyway, so it doesn't really matter. I think if you're searching for you'll find the first 57. And you don't have to worry about going through.
But he's still there, but you've now got a duplicate on there.
Yes.
So the question is do you want duplicates or do you want replacements? Which seems like the more reasonable thing to do.
Replacements?
Because you just know I'm gonna ask.
It's confusing, I think, if you have more than one of the same object.
What if you search for Fred?
Yeah.
How do you know which one you're gonna pull out?
You want the more current one, I imagine.
Suppose we have a programming language where I do this. Words sub friend equals some definition. And I do words sub friend equals better definition. What do you expect to happen? Should override it. How about if I do array sub 3 equals 20, array sub 3 equals 57?
Array sub 3 now equals 57.
It should change it, right? So if you're dealing with things that pretend that are arrays, you expect that if you change something at that array position, it should now have the different value. Well, the same thing is true here. You can think of hash tables as being basically arrays. So this is an array with that key, and if I change that key to something else at that position, because this is really just a number, I would still expect it to have the different thing. So it should do replacements. Okay, because then it behaves exactly like an array does. You just automatically replace values that are there. So the one thing that we have to do in our hash table is worry about when we put things into the table, are they already there? We actually have that code already
In the get.
in the get, because we already worry about if they're already there. So basically you can take almost this exact code, run through as a special case. If you find a replacement, here, we'll just do it. So that was that code there, and we did that right before here. And I need a table node. I probably used a pair again, I guess, or something, or what did I call it?
Yeah, you just it's already been sent.
Other pair. Let's call it other here for a second. That'll get me in trouble though. This should be other. And this should be other. Something along this line. So what we're going to do is we're going to run through the thing, and if we ever find a match, instead of returning something, we're going to say, we're just going to set the value like this. Other pair dot value. Do the replacement there equals whatever it was, value. So if we find a matching one, we'll just keep the node, do the replacement, and then return. Okay, so that's run through the table, see whether or not we can find a match. If we find a match, we replace the value. If we don't find a match, then we can just fall through and insert the existing one in at the starting position. Something along that line will take care of doing replacements. Okay? But basically that's all there is to hashcode, to a hash table. You ask somebody for a unique number, you don't care what that number is, you scale the number to the size of the table, stuff them into the table, hope that you don't get a lot of collisions because you've made your table large enough. If you do start to get collisions, you chain them onto each other, off you go. The only thing that we could do that's special here is if our table starts to fill up, we could grow. If the table's more than, say, 30% full, we could start to go, oh my God, we're going to have a lot of collisions, let's just make the table bigger. What happens if we don't grow the table?
Just get longer chains, I guess.
You get longer chains. So right now we have a table size of 100. The magic is that even if we don't grow the thing, all that happens is the performance suffers, because if you put 1,000 things in, then you just have probably chains of length 10 for each of the things on the chains, which means the maximum chain you have to search is 10. But if you want to keep the chains to length 1, then if you start to get about 30% full, you make the table bigger. If you make the table bigger, what do you have to do to go from old table to new table? There's a just in there that you said. Okay, it's not a matter like we did with arrays, where we just copied things over directly across to their equivalent positions in the new array. In this case, since you've made a larger array, you've got to get the hash code for every single thing, the magic number, and replace them in the table at a different position now, because the size of the table has changed, so you're going to scatter them all across a larger table. So you've got to go through your existing table, call hash code on every single thing, and replace them in the new table. Okay, so it's a little bit of effort, but it's fine. Okay, so what we'll do tomorrow is we'll do some actual applications of these hash tables to try to make them make sense now that we know how they work inside. And so I've got a couple of quick demos that we'll do for here's how I would use them. See you later.